Hello, good evening, Kaushik sir.
Yeah, good evening.
Okay, sir. Right, sir. Vasanta ma'am,
Sir, good evening, sir.
Yeah, good
ma'am,
evening.
you can start the session, ma'am.
Okay, okay, sir. Okay, thank you. Good evening, everyone. Welcome to the session 5 for day 3. It is my privilege to introduce our esteemed speaker for today's session of the FDP, Mr. Kaushik Bhargav Shivang. Sir is a dedicated software engineer and educator with a strong passion for coding and technology. Sir is currently serving as a member of technical staff at Salesforce. He brings extensive experiences in software development and instruction. Prior to this, he worked at Smart Interviews for nearly 4 years, progressing from software developer and instructor 1 to software developer instructor 2. His expertise spans various front-end frameworks, including Angular and Svelte, along with a solid understanding at Cloudflare and REST APIs. With a background in curriculum design and online instruction at QMath, Topper, and Cam K12. Sir combines his technical acumen with a commitment to mentoring and guiding aspiring developers. Without further ado, let's extend a warm welcome to Mr. Kaushik Bhargav to share his invaluable knowledge. Over to you, sir. Thank you.
Yeah, thank you very much, and good evening, all. So, is my voice audible to you, everyone?
Yes.
Yes, sir.
Okay, perfect. Okay, let me share the screen right now. I think my slides visible to you.
Yes, sir.
Okay. So, reinforcement learning fundamentals. I mean, this is the topic. So, we will going to discuss this session. So, we discuss the what is reinforcement learning example and applications of RL. RL stands for reinforcement learning, and the elements of RL. And we will see example like tic-tac-toe. So, I mean, this is application domain, and summing up with the history. So, firstly, we have to understand the terminology behind the RL. Then only we come into the history of RL part, and what is meant by the RL. Before starting to this, so actually, what we do while dealing with the traditional computer science. So we pass our inputs. I mean, we do the programming part. So we will do the some kind of the loops, and we pass to the a model or computer, and it will going to generate some logic. I mean, Boolean logic, zeros and ones. That means the compiler converting the high level user language to the uh, low level, and the like Boolean logic. And here, when we are dealing with the machine learning paradigm, so here we main aim is to pass the input and also the knowledge in the form of the labels to the model, and model will generate understand the patterns or nearby the feature. So for instance, if we would like to predict animal, so whether it will be cat or dog, by understanding the corresponding features, only it will I mean, with the help of the label and understanding generating such type of the patterns, only ultimately it will show outcome either cat or dog. So this is one kind of the learning which we call the as a supervised learning. And also we have the unsupervised learning. In the unsupervised one, we don't have such type of the labeling one, but we do all the clustering part, nearwise, all the features together, group together. That is how we do the labeling one. And we also have the semi-supervised, some sort of the labeling one in the, and we don't have the labels over there. And ultimately, we predict the final. Yep. And we will get the final outcome. And here comes the reinforcement learning. In the reinforcement learning, we don't have such type of the labelings. So the major aim is to we provide such environment where the agent can learn themselves by interacting with the environment. For instance, you can take infants have no explicit teacher, but direct sensory motor. So sensory motor is a term that describes the interaction between the sensory and motor aspects of the body. So it can also refer to the stage of cognitive development in infants and toddlers. So infant going to be going to be activate their cognitive ability by knowing whether if a infant going to choose either left side, so there is a fire or it can cause harm, it will get some penalty. And if he goes to the right side, he may achieve the reward, some kind of -1 +1, some kind of the reward. So this is some kind of learning, about the trial and error. So after getting either, if he gets his reward immediately to take the better action, so this will be the one possible, we can say some possible exploitation way. So if he gets the penalty and some kind of the exploration one, so this is the major, we have to balance between the exploration and exploitation, which is a major theme behind the RL. So this is how the agent here is the infant going to learn depending upon the experience, which will we call as the cause effect relationships, cause of actions. So we achieve the goals after reaching to the final destination. We will get some kind of the reward. And so major perspective here in RL, environment, the system or the world, an agent operates in. For instance, see the first picture where the person going to learn car. So this is one sort of the environment. So in the another picture, so this is some kind of the conversation. So see, so we have the two sort of the things. First one is the behavior and the target one. So target one means, so let us say if a person tries to communicate, the target means the discussion, some sort of the communication, and the behavior means the ultimate one. The surrounding persons going to involve means the how they respond, the environment going to respond to my my actions and my my target. So this is the major formula behind the environment. So we are aware of how our environment responds to what we do, and we seek to influence what happens through our behavior. So learning from the interaction. So foundational idea underlining nearly all theories of learning and intelligence. So depending upon the, so here environment going to respond our actions. So this is a major theme here in the environment. So next, so we explore reinforcement learning, a computational approach to learning from the interaction. We evaluate the effectiveness of our learning methodologies, and we adopt AI technologies. If you take any type of the applications, we use certain type of the methodologies in order to design the machines that effectively solve the learning problems. So the objective of RL is to maximize a numerical reward, which is the scalar one. So I mean, the reward which I told you earlier means the credits which we are going to get after taking certain actions or moving for a particular state, so which sort of the values we get. So certain kind of the reward signal. It may be the future states or cumulative sum of the scalar values which refers the reward signal, so which maps the situations to the actions. So I will let you know in depth these terminologies of RL. So as I told you earlier, so there are the two important features such as trial and error. So the learner is not told which action to take in each situation as in the supervised learning. As now we discussed about the supervised learning, we have the labeling such type of the teacher where the we have some idea which stage we are going to be selected in order to get the reward, and we have such type of the labelings in our hand, whereas in the RL, so we don't have such type of the predefined labelings, and depending upon the environment only, so which we face, we will came to know all these type of the course of actions, whether to choose a particular state or not, and also it discovered which action yields the most reward by trying of them only, by trying the particular actions only, exploration only. We came to know all these things. And the next one is the delayed reward. Actions may affect or not only the immediate reward, but also the next situation, and through that all subsequent rewards. So we are not only the focusing on the immediate reward. Hello. Yeah, we are not only focusing on the immediate reward, so which come from the adjacent states, but also we would like to understand the cumulative sum of such rewards. So we have to understand all these the states together, cumulative sum together. We have to know the all these scalar signal values, subsequent rewards, in order to update the current value only. The exploration is the major perspective behind such type of the delay rewards. So not to explore the each state, we come to know we will cover all kind of such feedbacks, all such type of the behaviors, etc. And these so RL is simultaneously a problem class of solution methods. So we have certain type of the solution methods for certain type of the problems where we don't have the labelings. and where we don't need to put don't like to put more training part. So this is the major platform, and we have to concentrate on these certain type of differentiations or the discrepancies when the dynamical system theory, optimal control of incomplete, when we deal with the MDP process. So MDP majorly concentrate on the model-based environment, where we come to know all the state, action, behaviors, value functions. But if it is the partial observable states, if we don't have the such type of the information in hand, incomplete, what we have to do, how we can handle those situations. So we have to make a cautious note, make a note on such type of the discrepancies. So this is the pictorial representation of the RL. I mean, main idea of the RL. So as I told earlier, see this is the full RL problem. So which consists of the various key components collectively defining how an agent learns to make decisions by interacting with an environment. So there are the various components such as agent, environment, states, actions, policy, reward, transition dynamics, value function, and so on, etc. First, agent means the entity that interacts with the environment and learns a policy to maximize rewards. So here, environment, the system or world the agent operates in, it provides the agent with states, rewards, and transition based on its actions. A set of all possible situations. I mean, whereas the state means, here state means a set of all possible situations the agent can find itself in. So which is kind of the set of the possible actions contains in the state, and each state provides information about the environment at a given time. So it contains the information, all the information which have to provide the input to the respond to the environment. And as I told earlier, which contains the action, which will be the set of all possible moves the agent moves can make. The agent selects an action based on its current state. So in the previous example, you can take infant example. Infant going to choose one particular going to provide a particular action, moves to the left side or right side, and he will get a penalty or a reward. So such kind of the actions are included in each state, and the policy is the another one. I mean, it is not there, but in the picture, but policy is the important one. So before understanding the reward, so policy, the strategy, policy means the strategy used by the agent to decide which action to take in each state. It maps state to actions. So we can denote it as the different perspectives. Either deterministic means it always selects the same action for a given state, irrespective to the state, it will select the same action. So, and then non-deterministic means next one, it will select the different action for a given state. and the stochastic or the randomness selects actions probabilistically. So these are comes under the policy. And then reward, as I told you earlier, from the starting onwards, reward means which is just like a scalar feedback signal given to the agent after taking an action. After taking an action, so a feedback signal given to the agent. So it tells the agent how good or bad the action was in that state. So, so that's how we came to know. Yeah. So we need to choose a particular action.
Please,
Other-
remaining all of you, unmute yourself.
Okay. That's how we came to know whether to choose a particular action or not. The here the agent's goal is to maximize the cumulative rewards over all the time. Means we can take that is a return one. So this is about the reward, and then we move towards the transition dynamics, which describes how the environment changes in the response to the agent's actions. So it usually defined as something kind of the probability, so which gives the probability of reaching the next state. So from a given state after taking a particular action. So this transition dynamic keeps changing depending upon the action, and then we also have the value function in additionally to that. So value function estimates how good it is for agent to be in a particular state. So which deals about the value function, and also we have the policy type of policy iteration, value iteration, which policy we choose and which policy in which policy we update the values. Value functions we will get, and then we covered the most of the things, and the discount factor, and we also have the discount factor. In the discount factor, whether the agent moved towards the nearest state rather than the further away. I mean, which is something range between 0 to 1. If we choose the near related one, how it would how we will get the corresponding feedback or scalar value, such type of things. So, and this is the one example, automatic car, self-driving car. In this experiment, so they have demonstrated a reinforcement learning algorithm to drive a automatic car system, and so we will see some. I will play some videos in the meanwhile. Next one is reinforcement learning versus the supervised learning. So as I told earlier, reinforcement learning is different from supervised learning. So supervised learning from a training set of the label, so which is contains like the external supervisor. So we have the labeling over there. So objective of supervised learning to generate an agent able to generalize its responses to act correctly in situations not present in the training set. So if we have the not adequate such type of the labelings, I mean, if we provide an environment, if we don't want to put huge stress to the agent, or we don't want to provide such type of the training, we will ultimately we choose the reinforcement learning. So we compared with the supervised and unsupervised. So in the unsupervised, we don't have such type of the labeling structure. So what we do in the unsupervised learning, we do the clustering part, and we group the near related one, or else we will compress all these inputs. I mean, noise, generating the noise, and we reconstruct to the original from. We have seen in the PCS such type of the autoregressive behavior. This is one kind of the unsupervised. I mean, these type in this type also we don't have such type of the labelings, just like the RL, but in this also we have to provide, we have to represent some type of the patterns. Whereas in the reinforcement learning we provide an environment, agent will come to know some of the dynamics. I mean, whether to know the dynamics or not. See, we have the different types of these modalities. I mean, different types of the. We can say different categories such as model based and model free. In the model based, here agent come to know such type of the dynamics. There will be some type of the knowledge behind to choose this state, or to achieve these adapt this type of the policy in order to get certain type of the rewards. And whereas the model free dynamics, where we don't have such a type of the understanding, where the agent come to know only performing such type of the behaviors. Which is another sort of another category. So the major aim is tries to reinforcement learning actually tries to maximize a reward signal instead of trying to find a hidden structure in the data set. As I now I have told you about the understanding the hidden structure and patterns in the previous supervised and unsupervised. Discovering a structure in the agent's experience is useful, but not address the problem of maximizing the reward signal. And previously we don't have such type of the maximizing such type of the reward signal. So we do such type of the understanding using this paradigm. So against the supervised and supervised learning. So another major concept is key challenge is there should be a balance between the exploration and exploitation, which is a key challenge in RL. So which is not present in other kind of learning. So if you take any type of the learning, the machine learning, deep learning, ultimate goal is the optimization. So ultimate, however, we have to minimize the cost function as much as possible, and to get the ultimate reward scores, the maximum reward scores as much as possible. We are trying to balance the exploration and exploitation. See, exploration means agent tries to explore each and every state. So whether it may be achieving the better reward one for one particular state, or which is the agent will don't bother, and they don't bother about all these kind of the stuff during the exploration, exploring the each and every state, irrespective the reward. It will, however, it will grab such things, such type of the scalar values, and then exploitation means the picking up the maximum value. Or if you take the multi-arm bandit, we are trying to pull the maximum arm. I mean, which arm, if I pull the which arm, I will get the maximum scalar reward, which is called as a exploitation. So we are choosing, we are going to, I mean, agent going to think about to get the highest reward. So, in summary, exploration selects actions never tried to a situation to learn what happens, how much reward they provide. So risky in terms of reward acquisition. So informative about environment dynamics and reward acquisition. So irrespective such type of the discrepancies, agent tries to move forward, explore as much as possible. And exploitation means select the actions already tried in the past and found to be effective in producing reward. So safe in terms of reward acquisition, not informative. Yeah. Yeah, please. I can see query from Nityasri. Yeah, please go ahead. Okay, I'm continuing the session. So, I mean, you take the example. If you visit any restaurant, if you explore, let us say, if you have, if you are going to visit 5 to 6 restaurant, up to 2 restaurant you explored, and you found better, I mean, better taste for your second restaurant, and you feel that that will be the some kind of exploitation, and you keep in mind, and for the next visit, you go for the B restaurant, I mean the second restaurant. This is the exploitation, and the major drawback is we may miss so other restaurants. Let us say remaining 3 restaurants. I mean, it may be taste better if we visit the different restaurants. This is the major drawback here, exploitation. And exploration. However, we have to visit each and every restaurant if food tastes good or bad. So we have to visit each and every restaurant, and we came to know how. That's how we came to know of the ultimate outcome. And then we have such a type of the dilemma for exploration and exploitation. The agent must try the variety of actions and progressively favor those that appears to be best. So one solution we can may choose the stochastic task. Each action must be tried many times to gain the reliable estimation of its expected reward. So still this dilemma is unsolved. So one thing we can balance these two things. I mean, depending upon such type of the prior experience only. So there is some concept here in the reply buffer and eligibility traces, where we solve such type of the issues. We will balance both the things together, or we can go for epsilon one. Epsilon one, where we balance these two things together, and we will see some of the applications. And RL agent can be also a component of larger system. Example, the agent that monitors the charge level of robots battery. In this case, the agent's environment is the rest of the robot together. This is one kind of the environment where the robot perform actions. That is how Cave Juno. Some type of the applications, we can say this is the robotic manipulation and interaction between the RL and other disciplines. And RL has substantial and fruitful interactions with other disciplines such as scientific and engineering disciplines. We apply in the various sort of the domains such as psychology, neuroscience, and optimization stats. Major theme behind the concept behind the RL is the something kind of psychology and the neuroscience. You deal with the cognitive behavior, and in the psychology, you know about the Pavlov's experiment. So whether to choose a particular to take the particular food depending on particular, you can take example particular food depending upon the experience. This is kind of the Pavlov experiment. So we have the various types here. While dealing with the such type of the psychological experiments, we have the stimulus, assuming the further state, and you take playing chess. So while playing chess, we think that whether a rook maybe move forward depending upon our projections, our plan, stimulus. So beforehand only we assume the steps, and depending upon that we will move forward or not. If we move one particular direction, what will happen, whether my route goes off or not. We will think such type of the stimulus as assumptions. So this will be the this ideology developed, similar kind of ideology developed in this RL. What I'm trying to say. So next we will see some of the examples and applications. As I discussed about the chess, first type of the opponent, you can see that while developing, I think the most of them played the online chess. This is the first invention where we apply the RL concept. Master check player makes. So developed by IBM's Deep Blue versus Kasparov, something. So where he, this grandmaster played opponent of Deep Blue related work, and then AlphaGo, which is another kind of the game where we are going to move these marbles, white marbles and black marbles. And something kind of the game we group we make a certain group using these marbles, and so which outperforms the application outperforms in the game of Go. We can call it as the AlphaGo, where we apply the RL concept. The 2016 it outperformed, and we know about the in these games, traditional games, online games, Artray, Backgammon, Blackjack, Tic-Tac-Toe, etc. And we use RL in the various, not only in the appliances, not only in the medical driving related environments, but we use in extracting the refineries operation and the cyber physical systems. And nowadays we are seeing these type of the appliances such as like the sweeping machines, where a mobile robot decides whether to enter a new room in a search of more trash to collect the trash. So if any barricade comes, it will generate its own instruction. This is one kind of the training, and it moves to the either right side or left side. It generates its own training. That's how it collects the trash. One kind of the appliance which we are seeing nowadays. And so I can tell you that one beautiful concept, research direction in RL, like robotic manipulation, whether the arm going to pick a particular product or particular one. You can see this robotic arm it going to pick up a particular type of the apparatus, resistor, transistors. It can be from the IC lab. Then these are the some sort of the example. We can also use control of the air quality, thermal comfort in a smart building. This is we also seen in the IoT. Something using the IoT, we can control all these qualities, all these facilities. In the same manner, we apply the RL over here in order to control such air quality or any sort of the things. So this is some sort of the adaptation before environment adaptation, and after environment, after understanding. So this is some kind of the I can say some kind of the readings, some kind of the maintenance while adapting such kind of the environments. So these are the examples. So autonomous cars, where we use the helicopter and the quadcopter control. So let us see. Stanford people, they developed these helicopter control. Let us see some. You can see some video I will display where they have used the RL concept here. So it automatically lands depending. It assigns all the stimulus by understanding the stimulus. It will where to choose a particular action or not. So see, this is a one kind of the RL. They have used the RL over here for autonomous helicopter, Stanford's helicopter. This is a one example I can tell you. See how it automatically trends. I mean, you can see that it is not crashing, right? Because depending upon the agent going to train itself whether to choose a particular action or not to get the particular policy. This is how they have considered. So, and next one is similar like Professor he explained quadcopter control. And the other examples and applications of RL, operation research, pricing, vehicle routing, something we applied the RL over there, and spoken dialogue systems chatbot. This is the one buzzword nowadays, chatbot creation. I mean, in Gen AI, we come over about creation of the chatbots. We use the RL over there. And then data
Good
center.
evening, sir. Good evening,
Yeah.
sir.
Yeah.
So, sorry to disturb in between, but actually, I am actually, sir, I need your suggestion and guidance regarding how to create this chatbot, sir. Any course materials for in connection with chatbot development? Could you please guide me how to the workflow process for creating a chatbot, sir?
Creating a chatbot. I mean, you know how to develop the websites. You created any websites, local websites, any local host.
No, sir. I have no prior experience, sir. Actually,
First,
I have.
yeah,
Yes, sir.
first you work on developing the websites, and then you learn understanding of the different packages over there, such as Fires, Bedrocks, while using the AWS.
Yes, sir. Yes, sir.
And yeah, you may refer the online courses on next. I mean, online material over there.
Yes, sir. Regarding creation of chatbot, sir.
Yeah, yeah. I mean, this is session is not on chatbot. I
Chatbot.
mean,
Yes, sir. I know, sir. Still, I wanted to have some guidance and suggestions regarding the same, sir. That's why.
yeah, yeah. You develop the website first, and you have the better. You will get the better intuition
Yes, sir.
to
Yes, sir.
work on the chatbots later on.
Yes, sir. Yes, sir. Yes, sir. Thank you, sir. Thank you.
Yeah. Next and so on, we will use on data center energy optimization, self-managing network routing systems, and the computation finance, etc. And the features shared among examples, interaction between the agent and environment. So the agent has a goal to whether to get a particular, reward or not, better reward or not. So there will be uncertainty about the environment, which effects of actions cannot be fully predicted. There will be uncertainty. As I told you earlier, there will be uncertainty when we talk about the partial. Margot diffusion process, such type of the partial assumptions we have, certain type of the uncertainty in such a type of the scenarios, and also action performed by agent affect the future state of the environment. So action something correlates with the future state. So if we big particular action, it will also reflect on the future achieving reward signal. This is I conveying you, and then presence of indirect and delayed consequences of actions. In the previous slides, we come over about the delayed signals and delayed responses. Where the agent not only focusing on the immediate one, and also thinking about the upcoming states to get all these rewards together, and agent use its experience to improve its performance over time, adjusting behavior such as the adaptation. So mainly about the trial and error. These are the elements. As I told you earlier about the policy one, so which defines the agent's way of behaving at a given time in a given situation. So policy, which is a crucial one, which is a strategy used by the agent to decide which action to take in a particular state. It maps the states and actions. It may be implemented as a function, lookup table, and such process. It may be deterministic or stochastic randomness. Deterministic means we are we already we have covered some sort of the things, such as we have the same sort of, we will go for the same sort of the value functions in each while taking the action for each state, rather than changing those values, where we see in the non-deterministic one, its generation is the target of RL reinforcement learning, and also see the policy is the important, and in that we have to know about the policy evaluation, policy iteration. So policy evaluation means the value function which how good it is for the agent for a particular value. We have to choose such type of the policies which is under the policy, what I'm trying to say. And in next one is the after evaluation, we can say the iterating or improvement until we are getting the better value in each policy, something kind of the iteration, right? We are going to discuss in the policy iteration, and then so the reward signal, the reward signal means which is kind of the scalar value which defines the goal of the RL. So at each step, the environment sends to the agent a signal number called a reward signal, immediate pleasure or pain, whether in any penalty or the reward. Some scalar value, some achievement which defines this type of the reward signal. The agent's objective is to maximize the total reward over all runs. That is how we define the cumulative sum of the rewards, which may be so this is also which may be the deterministic or stochastic functions of the state and action. So we can see the reward function which can be a state and action, and in so addition to that, I would like to mention about already I mentioned about some sort of the discount factor, which will be the something kind of the range and 0, 1 that it determines how much the future rewards are valued compared to the immediate rewards. This is how the lower values prioritize the short term gains, while higher values emphasize the long term rewards. What I'm trying to say that so this is something kind of the hierarchy. So we can say the hierarchical order. We have the short-term goals and long-term goals. Different components focus on the such type of the short-term goals and long-term goals depending upon the hierarchy. That is how we deal with the hierarchical or else. So ultimately, agent's objective is to maximize the expected cumulative reward or reward. So we often denoted by the such type of the discount factor. So then so value function, which is also a primary one, specifies what is good in long run, while the rewards focusing on what is good immediately. So which action is good, which policy is good we not to get the such rewards, which come under these type of the value functions. In this we also have something kind of the value type of the iteration, where we not going to deal with the policy. We will directly up this type of the value functions over there. And if we choose the policy values, we may opt for a particular type of the algorithms over there, where focus on the policy based algorithms, such as in the reinforce, where we avoid the values over there, and certain sort of the things we can choose the value of a state, which is the total amount of the reward an agent can expect to cumulative sum over the feature. The value of a state pair is the total amount of reward an agent can expect to cumulative over the feature and performing the action from the state. So a value here means the pairs of state and action. If we choose the which action corresponding to which state, we will get the total amount of the reward. And you need to focus on the two different sort of the things. That is, this is a bit confusing about the state action pair and the value action pair, where we focus on the combination of the value and action rather than understanding the state. We will just agent tries to focus which action we choose. We will get the ultimate values over there in the value action related one. Actually, while major mathematical intuition, we deal with the Bellman kind of the equation. In this, the RL for state value function. So in general, I'm touching the some sort of the mathematical intuition. Without this, we can't sum up this this RL. So simply we will take the Bellman equation for state value function. The Bellman equation is a fundamental recursive equation used in RL to describe the sorry, I mean, Bellman equation, which is some kind of the fundamental or rudimentary equation, which is used in the RL, describe the relation between the value of a state and value of its successor states. In order to update the value of a particular state, we also assume we will get the reverse signal. See, as I told you earlier, similar to some of the reverse, we are going to calculate in this type of the Bellman equation or Bellman optimality. This is major idea. I mean, major goal is to find the optimality. Which I mean, we have to trade off between those things, exploration and exploitation, and so similarly, we also do the Bellman equation for value function. So we will going to take the action value instead of the state value over there, and we find the optimal policy in this. I mean, in the both the action value or state value, state value. So this is about the Bellman optimality. Then so model of the environment. So before going to this, we will going to discuss about the process of the RL. I mean, we have the various categories over there. The starting from the initial state, the agent starts in some of the initial state, and then agent selects an action based upon its policy, and then the environment transitions to a new state based on the agent's action and transition dynamics. So the reward and then the agent receives a reward signal from the environment depending upon the transition, state transition and transition dynamics, which we already discussed. And then the agent updates its policy or value function based on the reward and state transition to improve future performance. Just now we spoke about the such type of the improvement. This is we called it as the learning, and the repeat the process continues until a terminal state is reached or maximum number of steps is taken. We can call it as planning. Planning means what course of action, and agent updates the policy, updates its policy means the learning. I mean, which is a major, which is another concept here in the RL. Next, the common, I mean, before talking with the model of the environment, so I would like to discuss about the common RL algorithms. First one is the model-free methods, which learn directly from experience without needing a model of the environment. And then model-based means they try to learn a model of the environment and use it to plan, such as like we discussed in the planning. So before the model-free methods, we will get the intuition behind the model-based. Try to learn the we have the model, and from that we learn the dynamics over there, such as we see in the DynaQ and the something kind of the MDPs. So model based, we have the all such type of the dynamics. So in MDP, we go for the deterministic and the stochastic one. Just like the randomers, we have the all the dynamic structure over there, and that's how we compute the finite state MDPs, finite state structures. And then on the other side, we will go for the model free methods, learn directly from the experience without interaction, without needing the intervention or interaction of model, such as agent came to know while interacting with the environment whether to choose a particular policy depending upon my prior experience only. So such type of the thing which we are going to see. For instance, you can take some kind of the Monte Carlo, Q-lining Monte Carlos, and and BQN. So where there is no involvement, such type of the models. If you take Monte Carlo trees, so something kind of the exploration it will do, agent will do, it will run till the end, and depending upon those feedback, my present state will be updated, and I move to the next state. I mean, we can say empty first visitors. I mean, Monte Carlo first visit, like that. I mean, depending upon these time steps, we update the values, and also on the other hand, Q-learning look for something kind of the greedy approach, which is in the these are things in the tabular form, right? Assuming the initialize it into the zeros, and we move to the further step, we grab the things, we achieve some reward, and we move to the next state. And in the SATSA and the state action reward, state action, we will opt for on policy and the off policy. So here, this is another concept. It came after dealing all these model free and model based methods. I mean, in the online based methods and the offline based methods, where in the, if you take the online based methods, so both the behavior and the target policy is same, which we discussed as a given example previously about the car driving and interaction related picture I mentioned about this type of the behavior and target policy. It becomes the same, but we are focusing on these should be the two different things, behavior and target policy. Keep saying two different things in the this type of the offline based structures. So for online based structures, you may choose the SATSA, and offline based structure you may choose Q-learning, and then we also have the deep learning. So deeply connected Q-learning network, which is some kind of the extension of the Q-learning, and then so model based methods, as I told you earlier about the MDP, I had given one idea. So here model of the environment, we have all the dynamics together. Models are used to plan, used for planning and choosing immediate actions, consider possible future situations, As I now told you earlier about the model-based RL methods, model-free RL methods, and this is extended example. So tic-tac-toe. So most of you play this tic-tac-toe. You want to construct a player that finds the imperfections in the opponent and learns how to maximize his chances to winning. So here comes in the picture of the some kind of the simulation where the agent going to have some kind of the assumptions whether to choose a particular state or not. So to maximize the chances of winning. So in this case, we implemented the RL, and we implemented the RL. Then classic techniques, we have a min-max solution from the game theory. Classic optimization methods such as the dynamic program need a complete specification of the opponent to work. In the dynamic program, which is kind of the model based, we categorize it into the sub problems. And for each sub problems, we will get some type of the scalar values for certain types of the policy behaviors, and we integrated them together. This is how the one particular solution here when dealing certain kind of situation. This information can be estimated from experience by playing many games against the opponent. So the idea is to learn the model of the opponent behavior from experience. So as I spoke about the this dynamic programming, which is kind of the model related methodology, where we have such type of the experience and behaviors, and we apply the dynamic programming to compute an optimal solution, not that different from what if you take the full RL related problem. Here RL stands for you can take the model free based methodologies and evolutionary methods would search the space of all possibility values for each policy considered in the population. Winning probability is computed by playing some games against the opponent. This is some kind of the traditional evolutionary methodologies where the probability is computed by playing some games. Some kind of experience, when we are playing against the opponent, better policies are selected during this evaluation. So, such as hill climbing policy, and this method could find the best policy, but it often inefficient using these evaluation methodologies. And then a method using the value function, which is kind of the lookup setup table here with a number of value for each state. The number is the latest estimation of win probability of that state. So which is kind of the we frame in an index over there for this is some kind of the evaluation method probability based estimation for tic-tac-toe. And you can see this is how the traces come over, simulation come over, whether opponent moves to a particular direction or not, to get the optimal solution here. This is a simulation. This is how the to get the maximum chances to get the reward best rewards or winning chances. This is kind of the lookup over here. Most of the time we move greedy approach. Occasionally we select the random, we'll select randomly, so such as exploratory moves. So while playing tic-tac-toe, we change the values of state in which we find ourselves, making them more accurate. To aim this, we back up the value of a state after each greedy move. Red arrows in the slide before something, we can tell like back prop over there. You can tell this is like the tree table or backup table here in the RL, where we store all these transactions in each and every move. This is like the backup, we call it as backup tree here. So this is the thing I'm trying to explain, the backup tree, red arrows in the slide before, and the value update. The current value of the earlier state is updated to be closer to the value of the later state. In a particular, we move the earlier state of a value a fraction on a way toward the value of later state. We store all these all these features together in each move. This is something kind of the Bellman optimality and something kind of the Bellman equation. So here v over s suffix t is the value function for state yes under a policy, and so all this value going to be stored in this policy. So alpha is something kind of the rate, something kind of, you can assume like the landing rate, and then so v over v suffix t plus 1 is next state, and we will get the corresponding values of the next state value. Alpha can be a smaller size value. We can do something kind of this will be the predefined values of hyperparameters. We can choose either. This is kind of the step size is to reduce the properly over the time method convergence for any fixed opponent to the true probability distribution of winning from each state given optimality by play by our player. So namely the method convergence to an optimal policy. So it will going to choose this will be the optimal policy over here. So for playing the specific opponent, if the step size parameter is not reduced to 0 over time, the policy can play well against the opponents that shows this change. So to get the optimal policy, this is kind of the you can try, you can experiment that. This is kind of the hyperparameter one. So you can take this example as model free one. You don't have such type of the behaviors. This is how the evolutionary methods use a fixed policy for several games to evaluate it and an unbiased way. happens during the games, and value function methods in context allow the individual states to evaluate, take advantage of information available during the course of play. This is how the value methods going to take all these transition dynamics in hand, more efficient in several cases. These are the general applicability of RL. Episodic containing of certain types of the states, which may be the continuous, and also RL work in the problem with no external opponent and game against the natural environment. Something kind of a applications. These are where we have the no external opponent. As I mentioned about the partial observable during the partial MDB. So this is of the history of the RL. There are main three threads: optimal control and learn of trial and error, and the psychology and the temporal difference learning, which mentioned in the early 19s between the current value and the actual value. You may come over during your machine learning models. This is how the hierarchy of what they achieved in each time zone, time period. In 1950, they come over the optimal control, designing to minimize and maximize a measure of control dynamic system. And mid 1950s, Richard developed. So this is he developed something kind of the Bellman equation. This is a major theme behind the dynamic programming, Markov decision process. And these are the things we already discussed: policy iteration and the optimal control learning connections. Ian's written work combines the learning and dynamic programming ideas in 1977 about the dynamic programming ideas regarding the various subproblems, as I told you earlier. And next, about some ideology about Q learning represents the full integration of dynamic programming and online learning. And next, you can see the Dimitri. He wrote a wonderful book. Some kind of theoretical intuition behind this RL, and he combined the dynamic programming and ANNs. He works mostly in the area of neurodynamics and also approximating the dynamic programming. And so optimal control is a part of RL, although the dynamic programming needs complete knowledge of the environment. So like learning methods, dynamic programming gradually synthesize the policy through the successive approximates. So as I told you earlier, so although this is a model perspective, there should be the analysis synthesizing certain types of the policy using some kind of approximation methods. This is the solution related theories to grasp this knowledge, and these are the prior things happened while they are learned during the idea of implementation of trial and error. And actually 1927 the reinforcement in the context of adapted from the context of animal learning in the previous slides, I explained about this kind of the animal behavior, and similarly 1961-63 and steps towards the AI and trial and error, and next about all these in the application of these tic-tac-toe and black chalk, and similarly the statistical learning, which is predominant in RL, and then so on and so forth. Yeah, you can see that these persons Sutton and Bartow, they develop such type of the actor critic architecture, adopting both the policy and value function over there. I can say that they are very prominent personalities in RL. So you can take, as I told you about the Sutton's, if you want to learn this RL part, you may go for a Sutton's and Bartow introduction to RL second edition, which is one beautiful book in the RL. You will get the more mathematical intuition, and if you work the neurodynamics, you can choose the Dimitri book. Yes, that is the end of the session. We discuss all the fundamentals of RL, and if you have any questions, you may discuss it. And thank you. One second. Hello? Yeah, I can see someone raise his hand. Yeah. Yeah, please, if you have any queries, you can, yeah, you can put in chat bot and you can interact with me directly.
Yes, sir. Good evening, sir. This is Chandar. Dheeraj, sir.
Yeah, good evening.
Yes, participant, do you have any doubts?
No, sir. No, sir. Thanks a lot, sir. Very nice session, sir.
Okay, thank you, sir. Ma'am, Basanta, madam, are you there?
Yes, sir. Yes, I'm here.
Okay.
Thank you,
you
sir.
want-
Thank you, sir. Thank you so much. I take this opportunity to express my heartfelt thanks to our esteemed speaker for his invaluable knowledge on reinforcement learning. Your
Yeah.
words, whatever the concepts you have covered, Sir has explained all the concepts related to RL, like the history of RL, objectives, the features of RL, and the elements in Markov decision process, differences between RL and unsupervised learning, key challenges like exploration and exploitation, and the examples and applications of RL, and the elements like policy, reward signal, value function, and model. Sir, your words have left us with great learning takeaways. Thank you, sir. Thank you so much for your valuable knowledge.
Yeah, thank you very
sir.
much giving the opportunity to discuss about the ARL. And thank you very much. And yeah,
Thank you, sir.
and quitting this session. Thank you so much. Bye.
Yeah, thank you so much, sir.
Thank you,
Thanks a
sir.
lot. Very good.
Thank you.